Good morning to all. I am Dr. T. Paradesi, Associate Professor, Department of Chemistry, SRM Institute of Science and Technology, Katangulathur campus. This video lecture presents an overview of analytical chemistry tailored for third BSc students. Analytical chemistry is the branch of chemistry deals with the separation, identification, and quantification. Okay. It's a traditional method to cover the chemical equilibrium and statistical treatment of data, especially in terms of qualitative and quantitative analysis. So the main focus of analytical chemistry is to separate the components. Normally, compound is comprised of various constituents. If you look at the pharmaceutical drug or intermediates, any compounds, it is composed of many molecules. So isolation of the individual component, that is the main focus of analytical chemistry. So this analytical chemistry is widely used in various industry like textile industry, even organic industry, and especially for pharmaceutical industry. So pharma industry people are using various techniques to isolate the components. So not only limited to isolation, identification. So that is one of the important aspects to understand the analytical chemistry. Identification means if you are synthesizing any product, first you have to identify whether the compound is the original one or not. So there are in olden days techniques are differ. Now there are a lot of advanced techniques. Say for example, if you are synthesized a drug, say for example paracetamol, you have prepared the paracetamol. How will you confirm? How will you identify? So the identification test is conducted by either by UV or IR. Okay, UV visible spectroscopy or infrared spectroscopy. And then after that you have to quantify. So these three things are important in the analytical chemistry: separation, identification, and quantification. Okay, so it should be confirmed with various parameter like qualitative analysis parameter, starting from the color, appearance, pH, LOD, so many parameters are there. Okay, right, now let us see one by one the classical method and the current method used in analytical chemistry. So first you should know what is analytes. The compound or chemical species to be measured or separated or under investigated. That is called analytes. Okay, so in olden days, this separation technique is used via either precipitation method or extraction, either liquid extraction, and then distillation. These are all the technique used in olden days. But nowadays, there are techniques like chromatography, electrophoresis. So if you look at in olden days, precipitation extraction means manually you have to do it. Whereas now, chromatographic techniques. Chromatographic techniques means if you want to analyze, isolate the people, isolate the components. So preparative chromatography is used. So the role of the preparative chromatography is if the compound is composed of 2, 3 or more than 2 components. With the help of this preparative chromatography, you can separate not only in the chromatogram, the real sample you can collect it at the end of the column. So you can, and after follow the procedure or methods, you can evaporate or something, some techniques you can use to isolate the individual component. So preparative chromatography is the best technique to separate the component. Olden days, some column chromatography techniques are there. This is a little bit advanced. And then qualitative analysis. Qualitative analysis means in previously the basic parameters are considered, like boiling point, melting point, refractive index, solubility. These are all the parameters used in the olden days. But now, for those things also, a lot of instrumentation techniques are used, like number of spectroscopy technique like UV, IR, NMR, mass spectrometry, X-ray diffraction. Okay, so many parameters are there. What is the criteria to choose an analytical method? So first we should think about the our goal of the content. So what type of information does we require for the analysis, and how the reproducibility and accuracy in this technique, how much sample is required, because most of the uh, time people will use some costly raw material or product. So in that case, the sample that should be recovered. Okay, so that is another important one. So how much sample is detected in the instrument, that is a limit of detection. Okay, so LOD, LOQ is another important aspect to consider, and the method is feasible, that is validated or not. So these are all the things we have to keep it in our mind before going to the analysis. Okay, then quantitative. Okay, so for this quantitative analysis, there are two different categories, whether complete analysis or partial analysis. So the goal is to determine amount of each component in a sample. Each and every component, what is the concentration? That is quantitative full analysis. Or else we need only two component or one component in the whole system. That is usually classified as partial analysis. Okay, so the method is different, depends upon the sample. We can choose the analytical methods. Okay, coming to the statistical data points. According to the International System of Units, 7 basic units are available actually. So what are the 7 basic units? Length, unit of length is meter, mass, kilogram, time, seconds, and the electric current, ampere, and the thermodynamic temperature, the unit of temperature is Kelvin. Amount of substance, usually represented amount of substance by mole, and then luminous intensity, that is candela. Okay, so these are the 7 basic units. So the same thing is displayed in a tabular column. What is the property of this analytes, and the unit and abbreviation are displayed in this slide. Okay, now coming to the next topic, derived units. Derived units are nothing. It is derived from the basic units, that is SI system of the unit. For example, if you look at area or volume, volume means usually volume should be represented in the meter cube. Okay, how it is represented in meter cube? Because it is derived from the basic units, that is length. Okay, so to calculate the volume of something, we should multiply the width, length, and height. So the width, length, and height all should be represented in SI unit, that is meter. So therefore the derived unit for volume is meter into meter into meter, that is meter cube. Okay, so similarly area, length, and width. Okay, so meter square. of the square. If you think about square, so length and width is multiplied. So length is expressed in meter, width is expressed in meter, so that meter square. So for area, meter square, volume, meter cube, and the speed, meter per second. Density, kilogram per meter cube. Similarly, force, kilogram meter per second square or Newton. Energy, usually energy is represented in the unit of joule or Newton meter, okay, or kilogram meter square by second square. These are all the derived units. And one more thing, dimensional analysis. Sometimes it is necessary to deal with the measurements that are very small, that is in the size of the atom, or very large number of atoms. So in these cases, it is often necessary to convert between unit of metric measurement. Okay, for example, a mass measured in gram may be more convenient to work with it if it was expressed in terms of milligram. So it depends upon the area or a required place. We have to use the appropriate units. Say for example, if somebody is asking to you, like how much quantity of water you will take a day. So if the question is raised, you can say your answer in the volume of how much volume you will take. So generally people will tell 1 liter or 2 liter or 3 liter. So here it should be, the answer is expressed in terms of liter. Suppose if somebody is asking to you how much volume of milk you have to take a day. So here you can say the unit of milk is ml, 100 ml, 200 ml or 300 ml. Okay, in case if you are doing HPLC analysis, how much volume of sample to be injected? Because so it depends upon the place, the unit is varied. So now if you look at the high performance liquid chromatography instrumentation, so the sample volume, the injection sample volume usually is very small. So it should be represented in microliter. So the volume in 3 different places, 3 different units, conversion is required. Okay, but standard unit is liter. Here it is liter, milliliter, microliter. Okay, right. So dimensional analysis is a method used to convert the unit by multiplying a given quantity by convention. Okay, so what are the steps to find out the dimensional parameter? Okay, so there are 3 steps to be followed. Okay, first we have to start with the given quantity and its units. Say for example, clearly the slide displays the simple basic example I have taken 500 centimeter to meter. If you look at how can you convert the 500 centimeter in terms of meter? So first we have to start with the given quantity. So 500 centimeter. Identify the desired unit, that is meter. So conversion factor, we know that 1 meter is equal to 100 centimeter. That is the conversion factor. 1 meter is equal to 100 centimeter. Right. Now, look at what is the question? 500 centimeter. So, 100 centimeter is equal to 1 meter. Then 500 centimeter is equal to 5 meter. That's all. Simple technique, simple method we can find out. Once we know the conversion factor, we can easily find out the dimensional parameter. Okay. Now, another simple question I'm asking: how many days? How many hours in 3 days? How many hours in 3 days? You should know the conversion factor, then only you can find out the answer. Very simple. I think this is a very quite common question. Common one, we know 1 day is equal to 24 hours. So 3 days means 3 into 24 hours, 72 hours. This is the simple one. And a little bit the example should be covered in terms of chemistry. Suppose if you are having a sample with a mass of 0.0034 gram. Okay, if you want to express the mass in terms of milligram, then what you have to do? So you can follow the previous one. 1000 milligram is equal to 1 gram, or you can say reversely, 1 gram is equal to 1000 milligram. Now the given data is 0.0034 gram. So find out 1 gram is equal to 1000 milligram, then 0.0034 gram is equal to 3.4 milligram. That's all. Okay, so once you know the conversion parameter, you can easily find out the answer. So some basic questions are displayed in this slide. You can work out later. Okay, so conversion to kilometer to meter, and liter to kiloliter, and gram to milligram, gram to microgram. So you can do it and work out with some examples. Right. Now let us move to the next topic, another important one, significant figure. The name itself you can understand, significance. Okay, so it is nothing but the digit in a number which carry meaning contribution to its precision. That is, it indicates the reliability of a measurement or calculation. So for understanding the significant figures is crucial for expressing the accuracy of numerical results and avoiding misleading interpretations. Look at the data 4.0123. Okay, so for this, what is the significant figure? There are more, totally 5 significant figures are there. The most important one is here. Look at 1, 2, 3. These are all the significant figures. So you cannot round off it. Right, now let us study about the rule. What are the rules? There are 5 set of rules to determine the significant figures. So you should follow all the 5 rules. Then you can identify or determine the significant figure of any data. Okay, but very simple. All are very simple steps. First thing, all non-zero digits are considered significant. All non-zero digits. That means any number from 1 to 9. From 1 to 9, the number will be considered as a significant figures. Say for example, 123.45. 123.45. All are non-zero digit. So all are significant figures. So how many significant figures in 123.4567? 7. 123.232? Whatever the number, non-zero digit are significant figures. First step. Then second step, 0 appearing anywhere between 2 non-zero digits are significant. Very simple. The 0, look at the left and right of the 0. Look at left and right of the 0. Both are digits. Then the 0 is also a significant figure. 0 appearing anywhere between 2 non-zero digits. That means left and right of 0 is a digit, non-zero. Then it is that 0 is considered as a significant figure. So simple example you can look at. 101 significant figure is 3. 10.1203 significant figure is 7. So any number in between center one is 0 or in between the 2 digits 0 is there, it should be considered as a significant figure. And then third one, leading zeros are not significant. Here the third one, leading zeros are not significant. Look at the example 0.000052. Okay, so these zeros are invalid, not significant figures. Only 5 and 2 are significant figures. Trailing zeros in a number containing a decimal point are significant. That means trailing zero, say for example 12.2300. So in this data, the decimal is there. That is very, very important. The number for which we are going to find out the significant figure, it should contain if it is containing a decimal point, then the zero is significant. If the data is containing a decimal, then the trailing zero is significant, otherwise not. So here the data gives 12.2300. So that the significant figure is 1, 2, 3, 4, 5, 6. All are significant figures. Suppose if you are taking the number 0.000122300, here the leading zeros are not significant, omitted. Decimal point is that, so that 122300, 6 figures, significant figures. Okay, suppose in case if there is no decimal point, leading zero is available, then it should not be considered. So look at 52300, there is no decimal, so that it has only 3 decimal points. Sorry, 3 significant figures. Okay, so some example is given. One slide only I will explain. Later, after that I will give some exercise to you later. So look at the figure 4308. 4 digits are there. 4 significant figures. All are. So if you look at 40.05, so the zeros are in between digits, so that it should be considered as a significant figures. And then 4,70,000. If you look at 4,70,000, trailing zero, but there is no decimal. Trailing zero, no decimal means it will not be zero will not be considered. So 2 significant figures. Whereas 4.00 decimal is there, so that trailing zero will be considered as a significant figure. So 3 significant figures. Yeah, this one is the best example to understand all those things. 0.00500 decimal is there, so that trailing zero will be considered. Leading zero will not be considered, so that 500 only will be considered for significant figures. So that the answer is 3. So likewise, many exercises are there. You can do it in your own way later. Okay, now let us move to the next topic, error analysis. Okay, so what is meant by error, and then what are all the types of error, what is accuracy and precision. Let us see one by one. Error, very simple. Error is nothing but the measured value and the true value difference. What are the difference between the real value and the observed value? Say for example, if you are finding out the assay of any substance. Okay, so your result is 99.5. Your result is 99.5. The original result is 99.9. So the error is 0.4. 0.4. So observed real value minus the minus observed value, that is error. Okay, so the error can be classified into 2 different types. One is determinate error, indeterminate errors. So it is also expressed in terms of a systematic error and a random error. Systematic error means it is consistently affect the measurements in the same direction, whereas the random error, it fluctuates unpredictability. So systematic error, say for example, if you are doing some titration, if you are carrying out a titration for your measurement, if you are using 10 ml pipette, 10 ml pipette, suppose if in the 10 ml pipette, suppose if you are if it is slightly broken at the tip, the bottom of the tip is slightly broken, the volume difference will be there. It may be not exactly 10 ml, maybe 9.95 ml, something difference will be there. But if you are using the same pipette for the whole set of analysis, okay, so the error will not much fluctuate. So consistently you are using the same thing, so there is a possibility to minimize the error. Okay. Then, but whereas a random error, it is not like that. Let us see one by one what are all the factors in the systematic and random error. Okay, so the first sources of systematic error is instrumentation and reagent error. Say for example, if you are using your analysis for the if you are using some kind of equipment or instrument is used for your regular analysis, if the instrument is not calibrated, then the result, you may get the wrong results. If the instrument is not calibrated or improperly calibrated, the result will vary. So that if you look at in industry, if you are finding out any equipment or instrument, definitely they will place the tag. Okay, so the tag consists of say for example UV visible spectroscopy. Okay, so according to their standard operating procedure, the instrument should be calibrated once in 6 months or 3 months, or the usage. Okay, once in 6 months means what is the previous date of calibration, what are the result data, whether it is passed or not. Okay, so the data will be placed on that instrument. So next calibration dates, everything will be available in the every instrument. It should be pasted or it should be tagged. So the calibration is one of the essential parameter to minimize the error. So if we are using the instrument which is not calibrated or improperly calibrated, it affects our results. Okay, then attack of foreign material. That means suppose if you are using any glassware, like it may be any reagent bottle or it may be a pipette or burette, okay, or conical flask, whatever it is. If any unwanted or foreign materials stick on the glass wall, slowly it may be carry out your analysis. It may affect your research. Okay, so there is a possibility of the error occurs. And then suppose if your reagent has some impurity, okay, either it may be a reagent or maybe your starting material or any byproducts if you are getting, so that may cause the error. These are all the category under instrumental error and reagent error. The next one is a personal error. That means most of the times it leads to color blindness. Say for example, volumetric titration, especially acid-base titration, you have to find out the appearance of pink color or disappearance of pink color. Sometimes for complexometric titration, you have to find out the steel blue color, wine red color, steel blue color, okay, reddish brown precipitate. So this type of color changes will be clearly notified. Okay, so suppose if the analyst has some color blindness, then it leads to error. Okay, so color blindness and then mechanical loss of material in various steps. Okay, so for the processing method, there is a possibility of loss of material. And then insufficient cooling of crucible. This is quite happen in the gravimetric analysis. For gravimetric analysis, we have to use the crucible for weighing the crucible, and then heat the crucible in the furnace, and then take it out. Again, put it into the desiccator. Slowly, it should be cooled down. So the cooling time should be monitored. Okay, so the same time to be used for the sample analysis. Okay, so for blank and sample, we should follow the same procedure. The error may be minimized. And then weighing. So mostly the measurement should be for the analytical chemistry. Weight, sometimes we may require a milligram level, sometimes microgram level. Okay, so milligram and gram level, we are using the balance. Okay, so the analytical balance should be maintained in a proper way. So the balance should be calibrated in a proper way, and then we have to frequently monitor whether any dust or impurity, any particles, unwanted particles on the pan, and then what kind of base you are taking for the measurement, and then how you are transferring the sample into your vessel. So mostly we are using butter paper to measure the solid sample. Okay, so we have to tear the butter paper. First, we have to check whether any unwanted materials in the butter paper. So it should be very clean. Then take the empty weights. Okay, tear it and pour your substance. While pouring the substance, transferring the substance, it should be very carefully. It should not be spilled on the pan. Then after that, close the door properly, and most importantly, you should check it. The fans are switched off, because sometimes your material will be very fluffy material, so it may leads to fly. Okay, especially for if you are measuring carbon nanotube, it's very difficult because it is a nano sized material. For measuring nano tube or any nano material, first before opening your bottle, switch off the fans. Okay, so the closed container, you have to wear the gloves and mask, everything. Then take the sample, even graphene oxide or CNT, transfer into the butter paper or whatever the material you want to take it. Okay, close the door properly and wait for some time to because while fluctuating the weight, don't take it. Okay, so wait for some time and write and note down the value. Okay, so these are all the basic things you should consider for the measurement. And then methodic error, this is very important. This can be rectified only based from the R&D team. For every industry, there will be an R&D team, research and development team. If there are any errors, any issues they are facing during the production, people will call the R&D people. They will identify the root cause of the problem and eliminate. Okay, sometimes it may be related to quality control also. Okay, so some examples are given here. Solubility of a precipitate in the solution in which it is prepared. Okay, so sometimes it's quite common. So if you are isolating the substance, and whether after isolation also some solubility will be found. Okay, so solubility of a precipitate in the solution in which it is precipitated. So this is the biggest challenge to isolate. Okay, so this kind of method will be rework and communicate to the production team. And decomposition of weighing form. Sometimes the product may be decomposed. Okay, so in that case also, the method should be modified. Like a similar way, hygroscopy, co-precipitation, and post-precipitation. The possibility of the formation of byproducts. So these are all the aspects. The method should be modified with the help of R&D team, research and development team. Okay, so we have studied systematic error, that is determinate error. Now let us move to random error, indeterminate error. Okay, so here there are four or five categories, 4 or 5 major sources are there. The first one is imperfection in measuring instrument or fluctuations in their performance. That may be due to the usage of the instrument. Suppose if the instrument is used continuously, or if there is any fluctuations in the power supply, the output will be dropped. Okay, so second thing, environmental factors. That means fluctuation in temperature. This is very important parameter, temperature. Okay, so we have to maintain. Suppose if the instrument should be placed only in the air conditioned room, then it should be air conditioned room. It should be maintained in a proper temperature. So that even if the column, suppose actually in some cases for even HPLC also. So HPLC should be always kept in a air conditioned room. But if you want to run your sample, the sample should be maintained in a 40-degree or 60-degree temperature or 80-degree temperature. Then instruments should be worked in air conditioned room. Should be installed in air conditioned room. But your sample should be analyzed in 60 degrees Celsius. There is a possibility the separate oven will be there. So you have to place the column into the oven. So the column alone should be maintained in the 80 degrees Celsius or 60 degrees Celsius. Even you can program it. Okay, so this is all the advanced technique we have. So the temperature should be maintained in a proper way. Okay, then human factor. Inherent limitations in our ability to read the scale most of the time. The measurement, mostly for the colored solution and the colorless solution, we have to follow the meniscus to measure the reading for the volumetric analysis. For volumetric analysis, colored solution, we have to follow the upper meniscus. Colorless solution, we have to follow the lower meniscus. So these are the things we should be very care to note down the readings. Okay, and not only limited to this measurement, many places there are possibility for human errors. And then method limitation, the same to the previous one. Here, inherent uncertainties in analytical method. So method itself wrong. That is the cases. It's very difficult to eliminate. Okay, method itself wrong means it's very tough to identify. Okay, wait, I think the previous one, yeah, accuracy and precision. Okay, accuracy is nothing but the degree of agreement between a measured value and the most probable or the true value. Okay, so how can we find out an experimental measure of accuracy? The difference between the result obtained by a method and the true or accepted value. That is accuracy. Okay, so it is related to absolute error. Absolute error means the real value minus the observed value. Accuracy is nothing but the real value minus the observed value, that is absolute error. Whereas relative error means the real value minus observed value divided by the real value. Okay, so observed value minus the real value divided by the real value multiplied by 100. That is called relative error. Relative error. Okay, right. Now, look at this image. You can clearly understand the concept of accuracy and precision. Precision is nothing but the reproducibility of the results. The degree to which an experimental result varies from one determination to the next one. Okay, so the results should be reproduced. If the results are reproduced, then your experiment or your analysis is very precise. Your data are very precise. If your let us see the example. First example. With this 4-4 diagram, we can clearly differentiate what is accuracy, what is precision. Okay, so look at the first one. Or look at first I will explain the last one, the fourth one, 1 2 3. This look at this fourth slide here. High accuracy and high precision. That means, see, look at in this circle, the inner circle, all the data are very close. All the data are very close. The center one may be the real value. Okay, so here how many measurements we have done? 3 plus 3 plus 6 plus 1, 7. There are 7 measurements we have carried out. For the 7 measurements, all the values are accurate and all the values are precise. This is the fourth slide. Whereas if you look at the third one here, the values are scattered. The values are scattered. That is very low precision. But okay, somehow accuracy is there, but the precision is not there. Whereas if you look at the second one, highly precise, the values are not accurate. It is beyond the accuracy level. It is beyond the accuracy level, but all the values are precise. All the values are precise. You are not getting the correct value, but whatever the measurement you have done, it is more precise. But that means your method is your results, the performance is correct. Your methods are something happened, so that you are getting high precision but low accuracy. The first one, there is no accuracy, no precision, because the values are scattered. The values are scattered. Okay, so accuracy means if your result is very close, if your result is very close to the true value, then it is more accurate. So your result is not close to the accurate, but your results 7 or 8 repeated measurements are very close. Then your data is very precise. Got it? Okay, right. So for this class, I studied a little bit about the introduction of analytical chemistry and what are the 7 basic units, derived units, and dimensional units. Followed by we have studied the significant figures. What are the significant figures and what are the steps to measure the significant figures? And then studied about the errors, that is determinate errors or indeterminate errors. And finally, we have studied about the accuracy and precision. Hope you understand the concept of introduction of analytical chemistry. Okay. Thanks for listening my class.